On the Pacific Northwest coast, there's a fault system that most people never see, rarely think about, and yet has the power to reshape an enormous stretch of the United States in minutes. It sits offshore, hidden beneath the Pacific Ocean, running from Northern California to Vancouver Island. For centuries, the coastline above it has looked peaceful. Forests grow, cities expand, highways carry millions of people, homes and businesses fill the valleys. But deep beneath the ocean floor, one tectonic plate is slowly being pushed underneath another, storing energy that will eventually be released. This is the Cascadia Subduction Zone. And scientists know something important about it that makes this story very different from a normal earthquake warning. They know it has produced enormous earthquakes before. They know the last great rupture happened on January 26, 1700, probably somewhere between magnitude 8.7 and 9.2. And they know that the geological record contains evidence of many earlier earthquakes stretching back thousands of years. But they do not know when the next one will happen. That distinction matters, because there is no scientific countdown clock hidden beneath Oregon or Washington. There is no instrument telling researchers that the fault will rupture next month, next year, or even within the next decade. What scientists can do is calculate the odds. And the latest U.S. Geological Survey assessment estimates roughly a 10 to 15% chance of an approximately magnitude 9 earthquake occurring on the Cascadia Subduction Zone during the next 50 years. That number may sound small, but for an event capable of producing catastrophic shaking and a major tsunami across the Pacific Northwest, even a probability measured in the low teens is impossible to ignore. And there is another reason scientists are paying attention. New research is raising a much bigger question about what might happen after a Cascadia earthquake begins, because the rupture may not be the only thing that matters. There is another enormous fault system farther south, the San Andreas. And scientists are now investigating whether a major Cascadia earthquake could influence activity along parts of that fault as well. To understand why, we first need to understand what Cascadia actually is. The Cascadia Subduction Zone stretches for more than 1,000 kilometers along the Pacific Northwest, from Northern California through Oregon and Washington, and northward toward Vancouver Island. It is a collision zone between the Juan de Fuca Plate and the North American Plate. The Juan de Fuca Plate is oceanic crust. It is denser than the continental crust of North America, so it is slowly being forced beneath the continent. The movement is incredibly slow, only a few centimeters per year. That sounds harmless, but over decades, centuries, and thousands of years, those centimeters add up. The problem is that the two plates do not always slide smoothly past one another. Large portions of the boundary can become locked. The plates continue trying to move, but the locked interface resists them. So instead of releasing all that movement gradually, the crust stores elastic strain. Think about bending a thick wooden ruler. You can push harder and harder without immediately seeing anything happen. The ruler simply stores energy, but eventually it snaps. The Earth's crust behaves differently because it is enormous and enormously complicated, but the basic idea is similar. Movement continues, stress accumulates, and eventually a locked section of the fault can rupture. When a rupture covers a huge portion of a subduction zone, the resulting earthquake can become a megathrust earthquake. These are among the largest earthquakes Earth can produce, and Cascadia has already produced one. On the night of January 26, 1700, something extraordinary happened beneath the Pacific Northwest. The coastline suddenly dropped. Trees that had been growing in coastal marshes were pushed into salt water. Sediment layers recorded a massive disturbance, and a tsunami crossed the Pacific Ocean. The most remarkable evidence came from Japan. People there recorded an unusual tsunami that arrived without the earthquake shaking that normally gives a nearby tsunami away. For centuries, nobody knew where that wave had come from. Eventually, scientists connected the Japanese historical records with geological evidence from the Pacific Northwest, tree rings, buried forests, tsunami deposits, coastal subsidence, and layers of sediment preserved on the ocean floor. Together, they pointed toward one enormous earthquake on January 26, 1700. The evidence is powerful because it comes from completely different sources. A tree does not know anything about earthquakes. A Japanese historian recording a tsunami did not know what was happening thousands of kilometers away. A layer of sand buried in a coastal marsh cannot tell scientists what caused it. But when all of these independent clues point toward the same event, the picture becomes remarkably clear. Cascadia has produced a great earthquake before, and it can do it again. The question is when. This is where things become more complicated. For a long time, people sometimes imagined great earthquakes as events that followed a predictable schedule. Wait a certain number of centuries, then the next earthquake arrives. But nature does not work like a calendar. The intervals between past Cascadia earthquakes vary. Some ruptures were probably shorter, some were much larger, and not every earthquake necessarily involved the entire subduction zone. Modern research shows that Cascadia is capable of producing earthquakes of different sizes depending on how much of the plate boundary ruptures. That means the statement, Cascadia is overdue can be misleading if it sounds like an appointment has been missed. The last great earthquake happened in 1700. More than 3 centuries have passed. But that does not mean the next earthquake is scheduled for today. Instead, scientists use the geological record to estimate probabilities, and those probabilities tell us that the hazard is real. The USGS estimates approximately a 10% chance under one model and about 15% under a time-dependent model for a full margin, approximately magnitude 9 event during the next 50 years. That is not a prediction. It is a risk estimate. And the difference between those two things is one of the most important parts of this story. But now we reach the discovery that makes the Cascadia story even more interesting. Researchers have been studying sediment preserved beneath the ocean floor. When large earthquakes happen underwater, they can trigger powerful submarine landslides and sediment flows called turbidity currents. Those currents race down underwater channels and leave deposits behind. Over thousands of years, those deposits become a geological record of past earthquakes. It is almost like a seismograph made of mud. Scientists can recover cores from the seafloor, examine the layers, date them, and compare deposits from different locations. And when researchers began looking farther south, toward the region influenced by the San Andreas Fault, something unexpected appeared. Some sediment deposits seemed to line up in time. The 2025 study, led by paleoseismologist Chris Goldfinger, examined evidence suggesting that earthquakes along Cascadia and the northern San Andreas may sometimes have occurred close together in time. In some cases, the researchers found paired deposits whose timing could be consistent with one earthquake occurring and another following within minutes or hours. That does not prove that every Cascadia earthquake triggers the San Andreas. It does not mean the two faults are permanently linked, and it certainly does not mean that a future Cascadia earthquake will automatically produce a San Andreas earthquake. But it raises a fascinating possibility. A major earthquake on one fault system could change the stress around another fault system. Imagine pushing on one side of a complicated structure. The force doesn't stay exactly where your hand touches it. It spreads through the structure. Some areas become more compressed, others become less stressed. And if another fault is already close to failure, even a relatively small change in stress could potentially matter. Scientists call this dynamic stress transfer and earthquake triggering. It is a well-established physical phenomenon. The difficult question is how important it would be in this particular region. And that is where the geological record becomes valuable. Because scientists aren't just asking what might happen in a computer simulation. They're looking for evidence that something similar may have happened in the past. The new research suggests that some deposits along the northern San Andreas and Cascadia regions may preserve evidence of closely timed events. The researchers interpreted these patterns as possible evidence of interactions between the two systems. If that interpretation holds up, it changes the story. Instead of thinking about Cascadia and the San Andreas as completely separate earthquake problems, scientists may need to consider them as neighboring systems capable of influencing one another under certain circumstances. That doesn't mean California should expect a second earthquake every time Cascadia moves. It means the possibility deserves serious investigation, and the stakes are enormous. A full margin Cascadia earthquake would already be a major disaster. The shaking could last for several minutes. That is a very long time when the ground beneath you is moving violently. Buildings would be stressed, bridges and roads could be damaged, power systems could fail, water and communications infrastructure could be disrupted, landslides could block transportation routes, and in some areas, liquefaction could cause water-saturated ground to temporarily lose much of its strength. But offshore, another process would be happening at the same time. The seafloor could move vertically, and when the ocean floor suddenly rises or falls over a huge area, it can displace an enormous volume of water. That is how a tsunami begins. The 1700 Cascadia earthquake left geological evidence of tsunami inundation along the Pacific Northwest coast, and modern modeling continues to examine what different rupture scenarios could produce. This is why coastal communities face a different problem from inland communities. If a major Cascadia earthquake happens offshore, the first warning for people near the coast may not be a phone alert. It may be the earthquake itself. And that is a crucial lesson from other subduction zone disasters around the world. When the shaking is strong and long-lasting near the coast, people cannot always afford to wait for someone to tell them what to do. The safest response in a tsunami-prone area may be to move immediately toward higher ground after severe shaking stops, following local evacuation guidance. Because a tsunami does not behave like an ordinary wave at the beach. It can arrive as a rapidly rising flood of water, carrying debris, vehicles, trees, and anything else caught in its path. And the first wave is not necessarily the largest. The danger can continue for hours. That is why scientists and emergency planners are not simply trying to predict the next Cascadia earthquake. They are also trying to reduce the consequences when it happens. One example is vertical tsunami evacuation. In some coastal communities, reaching naturally high ground quickly enough may be difficult. So engineers have begun designing structures that allow people to climb above the expected flood level. The concept is simple. If you cannot get to a hill, build a hill strong enough to survive the earthquake and stand above the water. That approach has already been used in parts of Washington state. The Shoalwater Bay Indian tribe built a tsunami vertical evacuation structure in Tokeland, Washington, designed to provide high ground for people who may otherwise have nowhere close enough to escape. This is the kind of preparation that becomes possible when scientists stop asking only, when will the earthquake happen? And start asking, what happens if it does? That shift is important because earthquake prediction remains beyond our current abilities. Scientists can measure tiny movements. They can monitor tremors. They can map faults beneath the seafloor. They can use GPS to measure how the crust is deforming. They can study sediments that are thousands of years old. They can reconstruct earthquakes that happened before modern civilization. But none of those tools currently gives us a reliable date for the next magnitude 9 earthquake. And that may be the most frustrating part of the entire story. We know the fault is active. We know the plates are moving. We know the region has produced enormous earthquakes. We know another one is possible. We can estimate its probability. We can model its shaking. We can model its tsunami. We can identify vulnerable communities, and we can build structures designed to survive it. But we cannot look at the fault today and say, it will break on this date. The Earth doesn't give us that information. What scientists are getting better at, however, is understanding the system itself. New ocean floor surveys are revealing the structure of the Cascadia margin in greater detail. Sediment cores are extending the earthquake record farther back through time. Computer models are testing thousands of possible rupture scenarios. GPS stations are measuring how the crust is moving today. And researchers are examining whether distant faults respond when major earthquakes occur nearby. All of these pieces are gradually turning an invisible hazard into something that can be measured. And the newest evidence about Cascadia and the northern San Andreas makes that picture even more complicated, because the biggest earthquake risk may not always be contained inside a single fault boundary. A rupture begins somewhere. Stress moves. Nearby structures respond. And sometimes the final earthquake may depend on what happens beyond the place where it started. That is the mystery scientists are still trying to solve. Could a Cascadia megathrust earthquake influence the San Andreas? The evidence says the possibility deserves serious attention, but the evidence does not say it will happen every time, and that distinction is essential. Because the most dangerous thing we could do with this research is turn a scientific possibility into a guaranteed disaster story. The real story is already dramatic enough. There is a massive fault system beneath the Pacific Northwest. It has produced earthquakes approaching magnitude 9. It produced a tsunami that crossed the Pacific in 1700. The geological record shows that great earthquakes have happened repeatedly over thousands of years, and modern USGS assessments estimate a measurable probability of another approximately magnitude 9 event within the next 50 years. Now, researchers are finding evidence that the consequences of such an earthquake might extend beyond Cascadia itself. That is the part we are only beginning to understand, and it changes the question. The question is no longer simply, when will the big one happen? It is also, how much of the West Coast could one earthquake influence? Because the Pacific Northwest and California are not isolated pieces of the Earth's crust. They are part of one enormous tectonic system. The same forces that slowly move the plates today have been operating for millions of years. They created the mountains. They shaped the coastline. They built the faults. And eventually, they will release the stress that has accumulated beneath them. We just don't know exactly when. That uncertainty can sound frightening. But it is also why preparation matters. You don't need to know the exact date of an earthquake to secure heavy furniture. You don't need a prediction to keep emergency water available. You don't need to know when Cascadia will rupture to learn your tsunami evacuation route if you live near the coast. And you don't need to believe that a disaster is imminent to recognize that preparation is cheaper and easier before the ground starts moving. For scientists, the goal is not to scare people. It is to make the unknown less unknown. Every sediment layer gives them another piece of the puzzle. Every GPS measurement shows how the crust is moving. Every earthquake provides another experiment conducted by nature. And every new model gives researchers another way to test what the geological record is telling them. The Cascadia Subduction Zone is still locked. The plates are still moving. The Pacific Northwest is still building cities, roads, bridges, ports, and homes above it. And somewhere beneath the ocean, the same tectonic process that produced the earthquake of 1700 is still operating. No one can tell us exactly when the next rupture will begin, but scientists can tell us that the possibility is real. They can tell us what the geological record reveals. They can estimate the probability. They can model the shaking. They can study the tsunami. And now they are asking whether the earthquake could interact with another major fault system hundreds of kilometers to the south. That is why Cascadia is not just an earthquake story. It is a story about how much we can learn from events that happened centuries before modern instruments existed. And it is a reminder that some of the biggest threats to modern civilization are not new at all. They are ancient processes happening beneath a modern world. The next great Cascadia earthquake could happen decades from now. It could happen sooner. It could be smaller than a full margin magnitude 9 rupture. Or, if a very large section of the fault breaks together, it could become one of the most consequential natural disasters in the history of the Pacific Northwest. Scientists cannot tell us which outcome will happen, but they are getting better at understanding the possibilities. And that may be the most important development of all, because we cannot stop tectonic plates from moving. We cannot lock the fault permanently. We cannot prevent an earthquake from releasing the energy that is accumulated underground, but we can study the evidence. We can build safer infrastructure. We can improve warning systems. We can create evacuation routes, and we can make sure that when the ground eventually moves, fewer people are caught completely unprepared. The Pacific Northwest has been quiet for more than 3 centuries, but quiet does not mean inactive. The plates are still moving. The fault is still there, and the geological record is still telling us what this coastline has experienced before. The next chapter has not been written yet, and nobody knows exactly when it will begin. If you want grounded, fact-first coverage of earthquakes, volcanoes, climate events, and the other forces changing our planet, subscribe to Wideview. And tell me in the comments, do you think the Pacific Northwest is prepared for a major Cascadia earthquake, or is there still far more work to do? Because we may never be able to predict the exact moment the Earth will move. But the more we understand what is happening beneath our feet, the better prepared we can be when it finally does.